Hello friends, I am Dr. Sangeeta Patil, Assistant Professor in the Department of Electrical and Electronics Engineering, MIT School of Computing, MIT ADT University. Welcome you all for a course on Basics of Transformer. Let us start the lecture. The transformer primary winding is connected to the AC supply, and due to that an alternating current flowing through it produces the alternating flux phi. This varying flux links with the secondary winding S through the core and produces EMF in it by mutual induction. Some of the flux also links with the primary winding also, and it will produces the EMF of the self induction in the primary winding. But friends, this flux produced by the primary winding while passing through the magnetic core links not only with the turns of the secondary winding but also the turns of the primary winding itself. Therefore, an EMF of self-induction is also induced in the primary winding. So, let us derive the mathematical expression for these EMFs induced in the primary and the secondary winding. So, let N1 is the number of turns of primary winding. Number of turns of primary winding. N2 are the number of turns of secondary winding. Let phi m is the maximum value of flux which is alternating in nature, which is linking with the both primary and the secondary winding in Webers. And let F is the frequency of supply in hertz, or we can say it as cycles per second. Okay. So here this figure shows the cycle of sinusoidal flux which is established in the core by sinusoidally varying alternating current which is circulated in the primary winding due to the applied voltage. So from this figure it is clearly seen that flux grows from 0 to its maximum value. So what is this? This is nothing but your phi m. 0 to the maximum value in 1/4 of the cycle, that is in time, which is equals to 1 upon 4f. Because what is the time for one cycle? It is 1 upon f. So what is the time for 1/4 cycle? It is 1 upon 4f seconds. We know that time period is nothing but the reciprocal of the frequency. So therefore, what is the average rate of change of flux? Rate of change of flux is nothing but phi m upon t. Okay. So what is the change in the flux is nothing but phi m minus 0. And what in how much time it is taking place? 1 upon 4f. 1 upon 4f. Then from Faraday's law of electromagnetic induction, what is the average EMF induced in each turn of the winding is nothing but average rate of change of flux that is equals to 4 phi m f volts. Why I have written like this? Because your E is nothing but minus n d phi by dt. Why minus? Because according to Lenz's law, this EMF is opposing the cause of producing it. So it will oppose the applied voltage. So timing will not consider this minus sign. So each turns means your number of turns is equal to 1 here. So this 4f will go on the upper hand side. So it will be 4 phi m f. Since the flux is assumed to be vary sinusoidally with the time, EMF induced by it in each turn of both the winding will also be sinusoidal. Now students, we know that for sine wave, what is your form factor? Form factor is nothing but 1.11 for sine wave. It is nothing but ratio of the RMS value to the average value. Ratio of the RMS value to the average value. Therefore, RMS value of EMF induced in each turn is equal to 1.11 into its average value. So what is the average value we have seen? So put the average value, that is 4 phi m f. So this is the RMS value of EMF induced in each turn. Okay. We know that RMS values are always denoted by the capital letter. Here we are talking about the primary. So I will write down 1 for the primary, 2 for the secondary winding. Okay. Now, if the transformer primary has n1 number of turns, therefore I can write down RMS value of EMF induced in primary winding of n1 turns equals to E1 equals to induced EMF per turn into number of primary turns So how many number of primary turns we have assumed? N1. So therefore I can write down E1 is equal to 4.44 phi m f n1 volts. Okay. Similarly, if N2 are the number of turns of the secondary winding, I can write down EMF induced in the secondary winding due to mutual inductance equals to 4.44 phi m f N2 volts. This is all about the EMF equation of the transformer. Now let us study about the voltage and current ratios of the transformer. So I have drawn the elementary transformer. This figure shows the transformer with the secondary winding connected to the load. So first of all, we'll start with the voltage ratio. We will start with the voltage ratio. So let N1 and N2 are the number of turns of primary and secondary winding respectively, and E1 and E2 are the RMS values of induced EMF in the corresponding winding. So we have studied now that E1 is equal to 4.44 phi m F N1 volts. Similarly, E2 is equal to 4.44 phi m F N2 volts. So voltage ratio is nothing but a ratio of the primary voltage to the secondary voltage. So I can write down E1 upon E2 equals to N1 upon N2 from the above equations if I take the ratios. Okay. So this is nothing but voltage ratio of the transformer or EMF ratio. So now if the voltage applied across the primary winding is V1 as shown in this figure, and the terminal voltage of the secondary winding is V2, then at no load, when your secondary is on open circuit, my V2 is approximately equals to E2. Okay. Also, if the primary current being very small under this condition, V1 is numerically almost equals to your self-induced EMF in the primary winding, that is E1. So, this above equation I can write down as E1 upon E2 equals to V1 upon V2 equals to N1 upon N2. N1 upon N2. So let us highlight this. The primary and secondary terminal voltages of a transformer are proportional to the respective number of the turns. So the ratio of the primary to secondary terminal voltage is nothing but your voltage ratio. So V1 by V2, which is approximately equals to E1 by E2, and N1 by N2 is called as the voltage ratio of the transformer. The second ratio is nothing but N1 by N2. So the ratio of the primary turns to secondary turns is known as the turns ratio of the transformer. So at no load, my voltage ratio is equals to the turns ratio. The impedance of the transformer winding being small, even at full load, we will assume the voltage ratio approximately equals to the turns ratio. Okay. So what is turns ratio? Turns, this is also equals to the turns ratio. So directly I am writing here, this is also equals to the turns ratio, because just I have said that the impedance of the transformer winding is small. So even at full load, we are assuming the voltage ratio equals to the turns ratio. Then third ratio other than voltage ratio and turns ratio, one important ratio I have to tell here, that is transformation ratio. Transformation ratio of the transformer. The ratio of the secondary voltage to the primary voltage. The ratio of the secondary voltage to the primary voltage is known as transformation ratio, and normally it is denoted by letter K. So transformation ratio K is nothing but ratio of the secondary voltage to the primary voltage. My secondary voltage is approximately equals to the secondary EMF, and primary voltage is approximately equals to the primary EMF. Also I can write down V2 upon V1 equals to E2 upon E1 equals to N2 upon N1 equals to N2 upon N1. Wait. Okay. So if, see, please listen here carefully. Now, if my K is less than 1, it means that V2 is less than V1. Means your secondary voltage is less than the primary voltage. So such type of transformer is called as step down transformer. It is that transformer which receives electrical energy at one voltage and delivered it at the lower voltage level. Okay. Then second point, if your K is greater than 1, that is your V2 is greater than V1, then such type of transformer is called as step up transformer. It is that transformer which receives the electrical energy at one voltage level and deliver it at the higher voltage level. Then third type of transformer, if K equals to 1, that is V2 is equal to V1. Such transformer is called as 1-to-1 transformer. 1-to-1 transformer. Such a transformer transfers electrical energy from one circuit to another circuit without any change in the voltage and its frequency also. Okay. Then fourth ratio, which is very important, it is nothing but the current ratio of the transformer. Current ratio of the transformer. Since the transformer transfers the electrical power from one circuit to another circuit very efficiently with negligible power loss. Why negligible power loss? Because in my first lecture only I have told you that transformer is a static device. There is no rotating part in this. So no more rotating losses. So transformer is a most efficient machine with negligible power loss. So I can write down power input equals to the power output neglecting the losses. So what is power input for AC? It is VI cos of phi. So for what is the power input? Primary voltage V1 into primary current I1 into cosine of angle between V1 and I1. Similarly, for output power I can write down V2 I2 cos of phi 2. V2 I2 cos of phi 2. Why? Because power formula we know. Power is nothing but VI cos of phi. So in this expression, I1 and I2 are the currents in the primary and secondary circuit respectively. And cos of phi 1 and cos of phi 2 are the corresponding power factors. But for transformer, primary and secondary power factors are almost nearly equal. So cos of phi 1 is approximately equals to cos of phi 2 for transformer. They are particularly at full load. Particularly this will happen at full load. Therefore, this above expression I can write down V1 I1 equals to V2 I2 equals to V2 I2. So I1 upon I2 is nothing but V2 upon V1. V2 upon V1. So combining the results that we have studied in the upper part, I can write down the transformation ratio as follows. What is transformation ratio? K. It is ratio of secondary voltage to the primary voltage, which is equals to E2 upon E1, which is equals to N2 upon N1. But in terms of current, what is V2 upon V1? It is nothing but the primary current upon secondary current. Primary current upon secondary current. So we have combined all the ratios and written the above expression. So from this expression, it is clear that the primary and the secondary currents of the transformer are inversely proportional to respective turns and the voltages. Okay. So The next is nothing but the rating of the transformer. Rating of the transformer. The next point in this lecture is nothing but rating of the transformer. When transformer transfers the electrical power from one circuit to another circuit, even though small, some energy is always lost in the transformer itself. And this energy appears in the form of heat, right? So this appears in the form of heat, raising the temperature of the transformer. So temperature increases due to heat. The temperature rise beyond the specified value is always harmful for the insulating materials which are used in the construction of the transformer. Therefore, students, it is the temperature rise which determines the capacity of the transformer. Since the heating caused by the current flowing through the windings mainly limits the output of the transformer, its rating is always specified in terms of kilovolt ampere, kVA, which is nothing but your kilovolts ampere. This is the output corresponding to the output current, giving the limiting temperature rise. The kVA rating of the transformer can therefore defined as the kVA output which it can deliver at the rated voltage and the frequency under usual service condition without increasing or without exceeding the standard limits of the temperature rise. So our transformer we have to design such that under full load conditions the temperature rise will not be excessive. So if consider a example of a 50 Hertz 250 kVA 1100 by 230 volt transformer. This is the rated capacity of the transformer. These are the primary and secondary voltage ratings of the transformer. Okay. So at rated full load, this transformer would be delivering safely 250 kVA at 230 volt 50 Hertz. What is the lowest rating here? 230 volt. So this transformer is capable of transferring the power or capable of delivering the 250 kVA at 230 volt 50 Hertz supply. So friends, the kVA rating of the transformer is given by kVA equals to V1 I1 upon 1000, or it is also equals to V2 I2 upon 1000. Why I have divided it 1000? Because volt amperes I have to convert it into kilovolt amperes. Kilovolt ampere. That's why I have divided it by 1000. Here V1 and V2 are the terminal voltages on primary and secondary side respectively, and I1 and I2 are the corresponding full load currents of the primary and secondary winding respectively. So students, I hope you understood the EMF equation and different ratios of the transformer. In next lecture, we will see the ideal transformer, the phasor diagram of ideal transformer on no load and on load. Okay, so if you like this lecture, please don't forget to like and share and to subscribe my channel. Thank you.